Every atom in your body is built from particles so small they make a grain of sand look like a planet. Inside those atoms sit quarks, tiny, trapped, and apparently breaking the rules of physics. We will see how quarks hold more than 99% of your mass, why the universe creates new matter just to keep them caged, and how recent experiments are cracking the rulebook that science has trusted for 50 years. If you enjoy this, like and subscribe. It helps more than you know. Stay awake. We begin.
Reach out and touch something solid. A desk, a wall, your own hand. It feels completely real, hard, dense, like something you can trust. Physicists will tell you that feeling is a lie. Every solid object you have ever touched is almost entirely empty space. The atoms making up your desk, your skin, your bones, they are almost completely hollow. If you took a single atom and blew it up to the size of a football stadium, the nucleus at the center would be the size of a marble. Everything else, just open air. But that marble is not the bottom of the rabbit hole. Inside that marble sit protons and neutrons. And inside those, smaller still, are the actual fundamental building blocks of all matter in the universe. Scientists call them quarks. They are so small that if a quark were the size of a grain of sand, a proton would be about as wide as a two-story house. There is no instrument on Earth that can see one directly. No microscope, no camera, nothing. And yet we know they exist. We know how many there are. We know how they behave. We know they carry forces and masses and properties that make them unlike anything else in nature. And we know something even stranger. Quarks absolutely refuse to exist alone. Every quark ever detected has been found locked together with other quarks, always partnered, always caged. A lone quark floating free in space has never once been observed in the entire history of scientific measurement. The universe appears to have built an unbreakable rule. Quarks travel in groups, or they do not travel at all. Here is what makes that rule so bizarre. Scientists have tried to break it. In machines stretching nearly 17 miles in circumference, physicists have smashed particles together at speeds approaching the speed of light, pumping in enough energy to vaporize small cities. They were trying to knock a single quark loose. Set one free, see what it looks like on its own. Every single time the universe found a way to stop them. The energy they blasted in did not free the quark. It created entirely new quarks from thin air, instantly pairing with the one they were trying to isolate. The universe essentially spawned new matter on the spot just to keep the rules intact. That is the world we are entering, a world where the smallest pieces of reality behave unlike anything at human scale, where forces operate 100,000 times smaller than the width of a single atom, where the rules that govern protons and neutrons directly determine how much mass you carry, how stable the ground beneath you is, and whether the atoms in your body hold together at all. Your body is made of atoms. Your atoms are made of protons and neutrons. Your protons and neutrons are made of quarks. And more than 99% of your physical mass does not come from the quarks themselves. It comes from the energy binding them together. You are mostly made of trapped energy. The particles contributing to your actual mass are almost negligible. That fact alone should make you question everything you think you know about what solid means. And yet the quarks themselves are only the beginning of the strangeness. Because understanding what quarks are requires understanding where the idea came from, and the story of how scientists discovered them is almost as strange as the particles themselves. For most of the 20th century, physicists thought they had matter figured out. Atoms were real, electrons were real, protons and neutrons were real. The periodic table organized everything neatly. Chemistry worked. Nuclear reactors worked. The system held. Then particle accelerators got powerful enough to smash protons apart, and everything got messy. Starting in the 1950s, physicists began discovering dozens of new particles inside the accelerators. Pions, kaons, lambda particles, sigmas, The list grew so fast and so chaotic that one Nobel Prize-winning physicist famously said that if he had known particle physics would turn into a zoo, he would have become a botanist instead. Nobody could explain why there were so many particles. Where were they all coming from? What did they have in common? Was there some deeper structure underneath all of them? Two scientists tackled that question at the same time, working independently, and both landed on the same answer in 1963. Murray Gell-Mann was a physicist at the California Institute of Technology who had already built a reputation for seeing mathematical patterns that other scientists missed. George Zweig was a young researcher working at the Nuclear Research Center in Switzerland. Neither knew what the other was doing. Both proposed the same radical idea. Protons and neutrons and all those zoo particles were built from smaller, more fundamental pieces. Gell-Mann called them quarks. Zweig called them aces. The physics community did not celebrate. They resisted. The problem was simple. If quarks existed, they should have a fractional electric charge. Every particle ever discovered up to that point had a whole number charge. Electrons carried exactly 1 unit of negative charge. Protons carried exactly 1 unit of positive charge. Clean numbers. Quarks, according to the math, should carry charges like 2/3 or -1/3, fractions that had never been seen before in nature, and to many physicists it seemed absurd. Some treated the quark idea as a useful mathematical shortcut, a way to organize the particle zoo without claiming the things were actually real. Then, in 1968, a team at the Stanford Linear Accelerator in California performed an experiment that changed the argument completely. They fired high-energy electrons directly at protons and watched how the electrons bounced off. If protons were smooth and uniform inside, the electrons would scatter gently and predictably. They did not scatter that way. The electrons bounced back hard in patterns that could only be explained by something small and dense sitting inside the proton. The proton had interior structure. There were things in there knocking the electrons around like a ball hitting hidden walls. Those things had the exact fractional charges the quark model predicted. Quarks were real, but accepting their existence opened a problem nobody had solved. If quarks had charges and mass, and could interact with electrons, why had no one ever detected a single quark flying freely through a detector? Every other particle discovered in an accelerator could eventually be seen on its own. Quarks never showed up alone. Something was holding them inside, something so powerful that no accelerator built by human hands could overcome it. The force responsible for that prison turned out to be the strongest force in the known universe, and the deeper physicists looked into it, the stranger it became. Murray Gell-Mann needed a name. He had the math, he had the model, he had a particle that existed inside protons and neutrons, carrying fractional electric charges, organizing the entire chaos of the particle zoo into a clean and logical system. He just needed something to call it. He landed on a sound first, a nonsense sound. Something like quirk. He liked the way it felt, strange and made up, for a particle that seemed to break every intuition about how matter should behave. He was planning to spell it that way, quirk, and move on. Then he opened a copy of James Joyce's novel Finnegan's Wake. The book is famously almost impossible to read. Joyce invented words, blended languages, and constructed sentences that work more as music than meaning. But buried in one passage, Gell-Mann found a line that stopped him. 3 quarks for muster mark. The word quark was right there. It sounded exactly like his made-up particle sound, and it appeared 3 times in the phrase, which matched his model almost perfectly, since protons are made of exactly 3 quarks. He took the word. The particle became a quark. What made Gell-Mann's contribution extraordinary was not just naming the particle, it was building the entire organizational system that made quarks make sense. He called it the Eightfold Way, a system grouping the chaotic zoo of particles into families based on shared patterns, much like the periodic table groups elements by their properties. When Gell-Mann arranged particles this way, certain spots in the pattern were empty. The math predicted a particle that had not been found yet. He described it publicly, gave its exact properties, and told physicists where to look. 2 years later, a team at Brookhaven National Laboratory found it exactly where he said it would be. That moment, predicting a particle and having it show up precisely on schedule, changed everything. The quark model stopped being a clever guess and started looking like a map of reality. George Zweig, who had worked out essentially the same model at the same time and called his particles ACEs, never got the same recognition. His paper was passed around in unpublished form and largely overlooked. The physics community had already attached the name quark to the idea, and Gell-Mann's version of the story became the official history. Science rarely hands out credit evenly, but the name survived because it captured something honest about the situation. Quarks are strange. They come in combinations that seem almost arbitrary. They carry properties with names like charm and strangeness, and bottom, chosen partly because physicists had run out of logical labels and started reaching for words that at least sounded interesting. The whimsy of the name matched the whimsy of the particles. Gell-Mann won the Nobel Prize in Physics in 1969, largely for this work. He spent the rest of his long career chasing a unified theory of everything, convinced that deeper patterns were still hiding beneath the surface of physics. He died in 2019, still searching. And the particles he named after a line from a nearly unreadable novel have turned out to be stranger than even he expected. Because quarks do not just come in one type, they come in 6, each one weirder than the last. Physicists call the different types of quarks flavors. That word is completely misleading. Quarks do not taste like anything. The name has nothing to do with food. It is just a label physicists chose because they had already used every other obvious word and needed something to distinguish 6 very different particles from one another. The 6 flavors are up, down, charm, strange, top, and bottom. The first 2, up and down, are the ones that build almost everything you can see and touch. They are the lightest quarks, the most stable, and they make up protons and neutrons. Everything from the iron in your blood to the calcium in your bones is built from these 2 flavors. The entire visible universe runs on up and down quarks. The other 4, charm, strange, top and bottom, are heavier and far less stable. They pop into existence during high-energy events like particle collisions or cosmic ray impacts, hang around for a tiny fraction of a second, and then break apart into lighter quarks. You do not encounter them in everyday life. The matter around you contains essentially none of them. Each flavor carries a different mass. Up and down quarks are nearly weightless at the subatomic scale. Strange quarks are roughly 100 times heavier. Charm quarks are heavier still. Bottom quarks weigh several times more than charm. And at the extreme end sits the top quark, which is the heaviest known fundamental particle in the universe. The top quark weighs about as much as an entire atom of gold. A single quark, roughly as heavy as a full gold atom. The comparison sounds impossible, but it is accurate. It carries almost all that mass in one point-like particle that is itself smaller than any measurement tool ever built. Each flavor also carries a slightly different electric charge. Up, charm, and top quarks carry a positive charge equal to 2/3 of a proton's charge. Down, strange, and bottom quarks carry a negative charge equal to 1/3. These fractions are what originally made the quark idea so hard for physicists to accept, since every other particle discovered before quarks carried whole number charges. What unites all 6 flavors is that none of them can exist alone. Every single quark, regardless of flavor, remains bound to other quarks at all times. The lightest and the heaviest, the most stable and the most fragile, all imprisoned by the same force. The 6 flavors also respond differently to certain particle interactions, and that variation is becoming one of the most important clues in modern physics. Recent experiments have caught bottom quarks behaving in ways they should not, decaying at rates the rule book says are impossible. That mystery will come back later, and it runs deep. For now, the key picture is this. 6 types of quarks exist. 2 of them build nearly all the matter in the universe, and all 6 are permanently trapped inside larger particles by a force so extreme that the universe would rather create new matter than allow even one quark to escape. The cage those quarks live in is not just strong, it gets stronger the harder you pull, and the particles responsible for building that cage are unlike anything else in physics. Protons are everywhere. Every hydrogen atom in every star in every galaxy carries exactly 1 proton. Every carbon atom in every living thing that has ever existed on Earth carries 6. The proton is one of the most common and most durable objects in the universe. Some physicists believe a proton might outlive the universe itself, holding together long after stars have burned out and galaxies have scattered. And every single proton, from the ones in your body to the ones at the edge of the observable universe, is built from the same simple recipe: 2 up quarks and 1 down quark. That is it. The entire recipe fits in one line. 2 particles carrying a positive charge of 2/3, plus 1 carrying a negative charge of 1/3. Add those charges together, 2/3 plus 2/3 minus 1/3, and you get exactly 1 full positive charge, which is exactly the charge of a proton, measured and confirmed millions of times over. Neutrons follow an equally simple recipe: 1 up quark and 2 down quarks, 1 positive 2/3 charge plus 2 negative 1/3 charges. Total charge 0. A neutron carries no electric charge, which matches every measurement ever taken. The elegance of those 2 recipes is almost unsettling. The universe builds its basic atomic material from combinations of just 2 quark flavors, following a recipe simple enough to memorize in 10 seconds. And it runs that same recipe for every proton and neutron across 100 billion galaxies. But there is a catch. The quarks themselves account for almost none of the proton's actual mass. Add up the masses of 2 up quarks and 1 down quark, and the total comes to roughly 2% of a proton's mass. The quarks inside are nearly weightless compared to the particle they form. Where does the other 98% come from? It comes from the energy of the force binding the quarks together. The act of holding those 3 quarks in formation requires so much energy that the energy itself contributes mass, because energy and mass are equivalent. This is the same principle at work in nuclear reactors and atomic bombs, just operating at a smaller and more fundamental level. You are not mostly made of matter, you are mostly made of binding energy in the form of mass. The quarks themselves are a tiny fraction of what you actually are, and the force creating all that binding energy operates at scales that are genuinely difficult to picture. If a proton were the size of Earth, the quarks inside would be smaller than a house. The space between them is not empty. It churns with particles popping in and out of existence, carrying force from quark to quark at unthinkable speeds. That force is the strong nuclear force. Physicists consider it the most powerful force in nature. It operates over a range so short that it has no effect on anything you have ever touched directly, and yet it is the reason anything you have ever touched holds together at all. The strong force builds the cage. And the cage, it turns out, is far stranger than the particles it holds. 4 forces run the universe. Gravity pulls planets into orbits and holds galaxies together. The electromagnetic force controls electricity, magnetism, and light. The weak nuclear force drives radioactive decay, and the strong nuclear force does something none of the others can. It holds the nucleus of every atom together against forces that should tear it apart. The strong force does not get much attention outside physics classrooms. Gravity and electromagnetism are the ones you feel every day. But in terms of raw power, the strong force wins by a staggering margin. Consider 2 protons sitting inside an atomic nucleus. Both carry a positive electric charge. Like charges repel each other, and the repulsion between those protons at the distances inside a nucleus is enormous. If you drop two protons close enough together with no other force involved, they would explode away from each other in a fraction of a second. Atomic nuclei do not explode. The strong force is why. At distances smaller than a proton's width, the strong force activates and completely overpowers the electric repulsion. It locks the protons together so tightly that separating them requires more energy than almost anything in chemistry or ordinary physics can provide. The strong force operates at ranges 100,000 times smaller than the width of a single atom. It is essentially invisible at human scale. Step even slightly outside its operating range, and it vanishes entirely. Inside that tiny zone, nothing can match it. The strong force is responsible for a fact that should genuinely surprise you. Every neutron and proton in your body, every one of those particles carrying the mass you feel when you step on a scale, holds together because of this force. Remove it, and atoms would fly apart. Matter as we know it stops existing. The concept of solid objects becomes meaningless. You are not held together by anything you can feel. You are held together by a force operating at scales roughly 100,000 times smaller than anything visible, running a process so fast and so powerful that physicists spent decades trying to even describe it mathematically. And here is the part that makes it genuinely strange. Every other fundamental force in the universe behaves the same general way. The further apart two objects are, the weaker the force between them. Gravity pulls harder between objects that are closer together. Magnets are stronger when they touch than when they are separated. The pattern holds everywhere you look. The strong force flips that rule completely. Pull the quarks inside a proton further apart, and the strong force pulling them back does not weaken. It stays the same, or grows stronger. The force does not fade with distance. It holds constant across the tiny range it governs, creating an effect that has no comparison anywhere else in nature. That effect is what makes quarks impossible to free, and it comes from a particle that carries the strong force between quarks, a particle unlike anything else in physics, one that can do something no other force carrier in the universe can do. Numbers alone cannot capture the gap between the strong force and everything else. Physicists use a system to compare forces, giving each one a strength value relative to the weakest force in nature, which is gravity. On that scale, gravity sits at 1, the weak nuclear force sits at roughly 10 to the power of 25 times stronger. Electromagnetism sits at roughly 10 to the power of 36 times stronger than gravity. The strong nuclear force sits at 100 times stronger than electromagnetism. Electromagnetism already runs every electrical device ever built, controls the structure of every chemical bond, and holds electrons to atoms across the entire universe. The strong force is 100 times more powerful than that. To feel what that means physically, imagine you are trying to pull a proton apart using electricity. You build the most powerful electric field ever generated and aim it at a proton. You push, nothing happens. The strong force laughs at your electric field. You would need to multiply the power of that field by roughly 100 just to begin competing. No technology humans have ever built comes close. The only way physicists have come close to testing the limits of the strong force is by slamming particles together at nearly the speed of light. At the Large Hadron Collider near Geneva, protons travel around a ring 17 miles in circumference at 99.999% of the speed of light before colliding. The energy released in those collisions briefly reaches conditions approaching those of the early universe. And still, the strong force does not simply give way. When the energy reaches the point where a quark might break free, something else happens instead, something the universe uses to enforce its own rules. The energy pumped into the system does not knock a quark out, it creates new quarks from the collision energy itself. Brand new particles materialize from pure energy, instantly pairing up with the quarks that were supposed to fly free. The strong force does not weaken under pressure. The universe reaches into its own reserves and manufactures new matter to keep the system intact. Physicists call this property of the strong force one of the deepest puzzles in fundamental physics. A force that refuses to let go. A force that recruits energy and turns it into matter rather than bending. A force operating at ranges so small that if you scaled a proton up to the size of a football field, the range of the strong force inside it would only cover the last few yards. The source of this extraordinary behavior is the particle that carries the strong force between quarks. Understanding what that particle does and why it works so differently from every other force carrier in nature is where the story takes its first genuinely strange turn. Quarks carry a property called color charge. It has absolutely nothing to do with color. Physicists borrowed the word because they needed a name for something with no real-world equivalent, and color happened to provide a useful set of labels. The property itself is invisible. It cannot be detected with the eye or any instrument that measures light. Calling it color is a convenience, nothing more. Every quark carries one of three color charges: red, green, or blue. Every antiquark, the mirror image counterpart of a quark, carries one of three anticolor charges: anti-iod, anti-green, or anti-blue. The rule governing color charge is strict. Any stable particle made of quarks must be color neutral. Color neutral means the colors cancel out, producing something called white, by analogy to mixing colored light. Three quarks, one red, one green, one blue, combine to white. A quark and its matching anticolor antiquark also combine to white. A proton satisfies the rule by holding one red, one green, and one blue quark. All three colors together cancel into color neutrality. That is one reason protons always hold exactly three quarks. The math of the color rule demands it. Here is where the story gets genuinely weird. The force between quarks does not depend on electric charge, it depends on color charge. Quarks are attracted to each other through the exchange of particles that carry color charge themselves. Those particles are called gluons. In electromagnetism, the particle carrying the force is a photon. Photons carry the electromagnetic force between charged objects, but photons carry no electric charge themselves. They are neutral. They transmit the force without participating in it. Gluons are completely different. They carry color charge directly. This distinction changes everything about how the strong force works. Because gluons carry color charge, they are themselves subject to the strong force. Gluons can interact with other gluons. They can pull on each other. They can form connections between themselves. The carriers of the force are also participants in the force, creating a system of staggering complexity. One consequence of this is that the strong force does not spread out in all directions the way electromagnetism does. Electromagnetic field lines fan outward from a charged particle like quills on a hedgehog, weakening as they spread. Gluons, because they attract each other, cannot fan out. They pull together into a narrow, concentrated tube of force directly between the quarks. That tube is one of the most extreme structures in nature. And what happens to that tube when you try to pull the quarks apart is the answer to one of the most persistent questions in physics. Most force carriers in physics follow a simple rule. They travel between two particles and deliver the force, and that is the end of their job. They are messengers, neutral, passive. Gluons break that rule completely. A gluon carries color charge. When it moves from one quark to another, it changes the color charge of both quarks it touches. A red quark emits a gluon carrying red color and anti-blue, and becomes a blue quark. The gluon lands on a blue quark and turns it red. The color charges swap. The quarks shift. The gluon is not just a messenger. It is an active participant in the system it is supposed to maintain. And because gluons carry color charge themselves, they attract other gluons. In electromagnetism, photons fly through space without interacting with each other. Two beams of light can pass through the same point and come out the other side unchanged. Photons are invisible to photons. Gluons are completely visible to other gluons. They interact. They exchange color charge with each other. They can bind together into temporary structures. A single gluon does not just zip from quark to quark and disappear. It participates in a dense, swirling network of interactions, tangled up with every other gluon in the system. The result inside a proton is genuinely chaotic. If you could somehow freeze a proton and look inside at a single moment, you would find the 3 quarks. But you would also find a roiling cloud of gluons constantly streaming between them, changing color charges, temporarily spawning quark-antiquark pairs out of pure energy, absorbing those pairs back, swapping color, emitting more gluons. The interior of a proton is violent and crowded in ways that the smooth, clean diagrams in textbooks cannot fully represent. There are 8 distinct types of gluons, each carrying a different combination of color and anticolor charges. Each type participates in different kinds of interactions. Together they create a color force field of extraordinary complexity. Here is the number that captures how extreme this gets. Physicists estimate that at any given moment, a proton contains not 3 quarks, but hundreds of virtual particles, quarks and gluons, constantly appearing and dissolving. The 3 quarks you learned about in school are real. They are called valence quarks, but they sit inside a quantum storm of additional particles that flash into existence and vanish before they can be directly detected. And all of those particles, all of those gluons and virtual quarks, are contained within a space smaller than a billionth of a millimeter. Because gluons attract each other, they cannot spread out. They bunch together into something called a flux tube, a concentrated rope of color force energy connecting the quarks, thin, dense, and impossibly powerful. When the quarks move apart, the tube stretches with them. What happens as that tube stretches is where the physics of quarks becomes genuinely unlike anything else in nature. Picture a proton sitting in space. Inside it, 3 quarks move around each other at speeds approaching a significant fraction of the speed of light. They are not sitting still. They orbit, bounce, shift, but they stay connected by something physicists call a flux tube, a dense cord of gluon energy linking each quark to the others. The flux tube is incredibly thin, far thinner than a proton itself. If you could see one at human scale, it would look like a taut string pulled tight between 2 points, thinner than a thread, carrying an immense concentration of energy per unit of length. Now imagine reaching in and pulling one of those quarks away from the group. As the quark moves, the flux tube stretches with it. This is where the strong force behaves unlike anything else in physics. Most forces radiate outward like ripples on a pond, spreading across space and weakening as they go. The gluon flux tube does not spread. It stays narrow. The energy in the tube does not dilute over distance. Instead, as the tube stretches, more energy packs into it. The force required to pull the quark further does not decrease. It stays constant. Every tiny increment of distance you pull the quark adds a fixed amount of energy to the tube. Physicists estimate that stretching a flux tube by a distance equal to the width of a single proton requires as much energy as lifting about 18 tons off the ground on Earth. To pull a quark just 1 inch would require more energy than every nuclear weapon ever built, combined. No machine humanity has ever constructed can deliver that. So physicists try with particle accelerators, smashing protons together hard enough to transfer enormous energy directly to the quarks. The flux tube stretches, the energy builds, and then something happens that makes the strong force unlike anything else in nature. The tube snaps. Or rather, it appears to snap. At the point where the energy stored in the tube becomes sufficient, the universe uses that energy to create something new. A quark-antiquark pair materializes directly from the energy in the tube, appearing at the point of maximum tension. One of those new quarks bonds with the quark being pulled away, the other bonds with the quarks left behind. The result, 2 protons where there was 1. The quark never escaped. The universe used the energy meant to free it to build new matter instead. This is happening constantly in particle accelerators around the world. Scientists pump in energy, trying to isolate quarks, and the universe keeps building new particles to maintain its rules. Every collision that produces a spray of new particles is the strong force enforcing the law of confinement by the most dramatic method imaginable. Yet there is a twist hiding inside this same force. At the very smallest scales inside a proton, the force that seems so absolute actually behaves in a completely unexpected way. Every force in the known universe weakens with distance, every single one. Gravity between two planets drops off as they drift apart. The magnetic pull between two objects fades as you separate them. The electric attraction between two charged particles weakens the further apart they get. This is such a consistent pattern across all of physics that it became one of the assumptions built into how scientists model nature. The strong force destroys that assumption entirely. Within the tiny range where it operates, the strong force holds constant as distance increases. Pull two quarks apart by a small amount, and the force pulling them back does not decrease. Move them apart a little more, and the force may grow slightly stronger. The energy in the flux tube between them builds, packed tighter and more concentrated, creating a tension that works exactly like a rubber band. Except a rubber band eventually snaps. It has a breaking point. Stretch it far enough and it loses its structure and tears. The flux tube never tears in a way that sets a quark free. The reason comes down to a simple but devastating piece of physics. Creating a break in the flux tube requires less energy than maintaining one. The moment the tube reaches the point where it might snap, the energy it contains is already sufficient to create new quarks. The universe fills the break before it becomes a real opening. Two new particles appear. The ends of the tube seal themselves, and the quark that was almost free is immediately captured again. Every time, without exception, in every experiment ever attempted. The rubber band analogy only goes so far, because it implies a passive structure. The flux tube is active. It constantly recreates itself. When you pull on it, it pulls back. When you stretch it to breaking, it multiplies. It is a system that uses your own effort against you, turning the energy you apply into new matter that reinforces the cage. This behavior is one of the reasons physicists call color confinement one of the deepest unsolved problems in science. Not because they doubt it is real, every experiment confirms it, but because no one has yet written the exact mathematical proof explaining why it must be true. The universe has a rule so strict it rebuilds matter to enforce it, and the fundamental equation proving why that rule exists has not been written yet. Something deep is hiding in there, and the deeper physicists looked into how the strong force actually works at the very shortest distances, the more unexpected the picture became. Here is the contradiction at the heart of the strong force. Pull quarks apart, and the force between them grows. The further apart they get, the harder it pulls them back together. That is what we just covered. It seems to suggest that quarks are bound in the tightest, most relentless grip imaginable, that every quark inside every proton is constantly straining against a force that refuses to ease up. But zoom in closer. Watch the quarks at the very center of the proton, almost touching each other. At those extreme short distances, the strong force nearly disappears. Quarks that are close together barely feel the strong force at all. They move around the interior of the proton almost freely, like passengers in a wide-open room. The closer together two quarks get, the weaker the force between them becomes. Deep inside the proton, at distances far smaller than the proton's own width, quarks behave as though they are completely unbound. This seems impossible. The same force that becomes nearly unbreakable at medium range almost vanishes at close range. Physicists call this behavior asymptotic freedom. The word asymptotic means approaching but never quite reaching. Quarks inside a proton approach freedom as they get closer together, but they never actually achieve it. The moment they drift slightly apart, the force snaps back. The result is a strange and contradictory life inside a proton. Quarks move around with relative freedom when they are close to each other, experiencing little resistance. Wander a bit further out toward the edge of the proton, and the pull strengthens dramatically. Move toward the surface of the proton, and the force becomes overwhelming. It is like a prisoner in a room where the walls are made of rubber. Near the center, almost no resistance. Walk toward the wall and it gradually pushes back. Reach the wall, and you cannot move it at all. This discovery was so unexpected that it fundamentally changed how physicists understood the strong force. Two researchers, David Gross and Frank Wilczek, and independently David Politzer, worked out the mathematics in 1973, showing that the strong force coupling, its effective strength, actually decreases at shorter distances. This runs opposite to every other known force. The discovery earned them the Nobel Prize in Physics in 2004. Asymptotic freedom also explained why early experiments at the Stanford Accelerator could probe the interior of a proton using high-energy electrons and find quarks that looked almost free. At the high energies of those experiments, the electrons were effectively probing very short distances inside the proton. At those distances, quarks barely resisted being poked at. But probe at lower energies, look at larger scales, and the quarks are absolutely trapped. The same particle, the same force. Two completely opposite behaviors depending only on how close you look. That duality hides something remarkable about how the universe decides what is free and what is caged. David Politzer was a graduate student at Harvard in 1973 when he stumbled onto one of the most important results in the history of physics. He was calculating how the strong force changes at different energy scales, working through dense mathematics that described how particles called quarks interact with the gluons carrying the force between them. The calculation was tedious, the math was complicated, and when Politzer finished and looked at his result, he thought he had made an error. The number said that the strong force gets weaker the shorter the distance you examine. That was backward. Every other force in nature gets stronger as you compress it into a smaller range. The strong force appeared to do the opposite at very short distances. He checked his work. He got the same answer. At the same time, across the country in Princeton, Frank Wilczek was running the same calculation under the supervision of his advisor David Gross. Gross had started the project partly convinced that the calculation would show the strong force getting stronger at short range, confirming the existing understanding. Instead, Wilczek kept getting a negative sign in the result. The coupling was decreasing. The force was weakening at short distances. Gross and Wilczek double-checked. Politzer double-checked. Both groups arrived at the same conclusion independently. The strong force does something no other force does. It eases off at close range. The three physicists published their results, and the physics world had to absorb a completely new picture of how quarks behave. Inside a proton, quarks are nearly free when they are close together. Drag them toward the edge of the proton and the force snaps back like a tightening chain. The force is distance-dependent in a way that runs backward compared to everything else. This also explained a puzzle that had been sitting in experimental data since the Stanford electron scattering experiments in 1968. Those experiments had fired electrons into protons at high energy, and the quarks inside had scattered the electrons as if the quarks were moving freely, barely attached to anything. For years, physicists could not explain how quarks could be so tightly confined, yet look so loose when probed at high energy. Asymptotic freedom was the answer. High-energy probes mean short distances. At short distances, quarks are nearly free. At longer distances, the trap snaps shut. For their work, Gross, Politzer, and Wilczek shared the Nobel Prize in Physics in 2004. The award citation described their discovery as unlocking a hidden key to the structure of matter. But asymptotic freedom was only half the picture. It explained why quarks look free up close. It said nothing about what happens when you try to drag one out completely. And that question, what actually happens when you attempt to rip a quark out of a proton, leads to one of the most spectacular things the universe does to enforce its own rules. Every particle accelerator ever built has, in some sense, been trying to break quarks free. When physicists at the Large Hadron Collider in Switzerland slam protons together at near-light speed, they are pumping extraordinary amounts of energy into a system built around quarks. The collisions happen at energies millions of times greater than anything a chemical reaction could produce. In the moments after impact, the quarks inside those protons receive more energy than almost any particle has ever received in a controlled experiment. And still, not a single lone quark has ever been detected flying out of one of those collisions. Here is exactly what happens instead. As the energy of a collision reaches the quarks, the flux tube connecting them stretches. The energy stored in that tube climbs rapidly. The force pulling the quarks back toward each other does not weaken. It holds. If the collision is powerful enough, the tube approaches its limit. And right at that threshold, the tube does not release a quark. It converts. The energy stored in the stretched tube is so enormous that it crosses the threshold described by the equivalence of mass and energy. All that stored energy spontaneously becomes two particles, a quark and an antiquark, materializing directly from the energy in the space between the separating quarks. This happens in a timescale far too short to measure directly. The new quark immediately bonds with the quark that was being pulled away. The new antiquark bonds with the quarks left behind. Instead of one proton with a quark escaping, there are now two particles, each containing properly confined quarks. The universe has created new matter from energy to prevent a rule violation. In the spray of particles erupting from a high-energy collision at an accelerator, physicists can observe this process indirectly. They detect not a lone quark, but a tight jet of newly created particles, a cluster of matter that formed when the flux tube snapped, and new quarks materialized. These jets carry the direction and energy of the original quarks. Scientists map them carefully because they are the closest thing to a quark footprint that physics allows. Detecting these jets has become one of the primary tools for studying quark behavior. Physicists trace the jet, reconstruct the properties of the original quark that produced it, and use those properties to test the theories. What they keep finding confirms the confinement rule again and again. Lone quarks never appear. The universe always intervenes, always manufactures new matter, always seals the cage. But the cage itself has a secret. The particles popping into existence to seal the tubes are not the only virtual particles crowding the interior of a proton. There is an entire invisible sea of quarks and antiquarks inside a proton at all times, appearing and dissolving before anyone can directly detect them. And this sea is directly connected to one of the most strange facts about your own body. What you just heard about flux tubes breaking and new quarks appearing is not a rare event, limited to particle accelerators. It is happening everywhere, all the time. Inside every proton in every atom in the universe, the energy of the gluon field is so intense that it constantly brushes against the threshold required to create new particles. Quantum mechanics allows particles to appear from empty space as long as they vanish quickly enough that the energy books balance out. These temporary particles are called virtual particles, and the interior of a proton is full of them. Virtual quark-antiquark pairs pop into existence, persist for an almost impossibly brief moment, and then annihilate back into energy. They leave no trace that can be directly measured, but they affect the quarks around them. They contribute to the proton's properties. They add to the chaos of the system. Physicists estimate that at any given instant, a proton contains far more than 3 quarks. The 3 permanent quarks, called valence quarks, sit inside a boiling sea of virtual quark pairs that continuously flash in and out of existence. This sea is real in the sense that it affects measurements. Hit a proton with a high-energy electron, and you do not just bounce off 3 quarks. You sometimes hit a virtual quark that happened to be in the wrong place at the wrong time. The pair creation process becomes concrete and real rather than virtual when the energy input is high enough. In an accelerator collision, the energy is so extreme that virtual pairs can receive enough of a boost to become real permanent particles. At that point, the pair is no longer borrowing energy from quantum mechanics for a brief moment. The energy input has given them enough mass to persist indefinitely. They become real quarks and antiquarks, instantly swept up into the confinement system. This process is how the universe converts energy directly into matter. It is the same fundamental process that physicists believe filled the early universe with particles in the moments after the Big Bang. The universe was so hot and so energetic that pair creation happened continuously and rapidly, building up the matter that eventually formed stars, planets, and everything alive. Every proton in your body is still running a quieter version of that same process. Inside each one, virtual quarks flicker in and out. Gluons stream between them. Color charges shift and swap. The 3 valence quarks ride in the middle of this storm, permanently confined, surrounded by fleeting shadows of new matter that form and dissolve before they can leave. The scale of that confinement is extreme. No particle ever breaks out. The storm inside never stops, and the energy required to maintain it is a direct physical cost, one that shows up in the mass you carry every time you step on a scale. But what about the quark that weighs so much it cannot even afford to stay trapped? Stand on a scale, whatever number it shows, nearly all of it comes from something invisible. It comes from energy. The quarks inside your protons and neutrons are almost weightless at the scale of a proton. The 2 up quarks and 1 down quark inside a single proton, if you weighed them in isolation, would account for roughly 2% of that proton's actual mass. The 3 quarks in a neutron contribute a similar tiny fraction. The other 98% comes from the energy of the gluon field binding those quarks together, energy that has become mass because of the relationship discovered by Einstein. Energy and mass are 2 forms of the same thing. A system containing enormous amounts of energy has more mass than the same system at rest with less energy. The gluon field inside a proton is so energetic, so packed with moving gluons, virtual pairs, and color charge interactions, that the energy itself contributes almost all of the proton's mass. Your body contains roughly 7 billion protons. Each one of those protons is almost entirely made of binding energy, masquerading as mass. If you remove the gluon field from every proton in your body, leaving only the quarks, your mass would drop to roughly 2% of what it is now. You would weigh almost nothing. The chair you sit on, the floor beneath you, the earth itself, the same calculation applies to all of it. Every piece of ordinary matter in the universe carries mass that is overwhelmingly the result of strong force binding energy. The actual particles inside are a small fraction of the total. This is one of the most counterintuitive results in all of physics. We think of mass as something inherent to particles, something they carry around as a fundamental property. Quarks have mass in their own right. Electrons have mass. But the mass of the matter you interact with daily is dominated by a dynamic, energetic process happening inside every atom, not by the static properties of the particles themselves. The proton's mass is an emergent property. It arises from a system in constant motion, from gluons racing between quarks, from virtual particles popping in and out, from the enormous tension in a color field stretched to its limits. The proton does not sit still. Its mass is the result of a storm. Every atom in your body is housing that storm. Every atom is mostly energy, shaped by confinement into the hard, stable objects you walk on, and breathe, and hold. And among the quarks involved in all of this, there is one that breaks the rules almost immediately after it forms. One quark so massive, so far beyond the others in scale that the strong force itself cannot trap it before it disappears. Every quark obeys the law of confinement. Every quark except one. The top quark is the heaviest fundamental particle ever discovered. It weighs about as much as an entire atom of gold, one particle, matching the mass of one of the heaviest atoms on the periodic table. That comparison is staggering when you consider that a gold atom contains 79 protons, 79 electrons, and more than 100 neutrons, while the top quark is a single point-like particle with no detectable internal structure. Physicists did not find the top quark until 1995 at the Fermilab accelerator outside Chicago. The reason it took so long to detect is the same reason it defies confinement. It is so massive that producing one requires an enormous amount of energy, and it survives for an almost impossibly short time once it appears. The top quark decays in less than 1/10,000th of a trillionth of a second. To feel how fast that is, the strong force needs a certain amount of time to form the flux tube connections that would cage the quark inside a composite particle. That process happens extremely fast at the subatomic scale, but the top quark decays faster still. It breaks apart through the weak nuclear force before the strong force can establish a grip on it. The top quark is the only quark in the universe that never gets trapped in a proton or neutron or any other composite particle. It exists briefly, decays, and leaves behind lighter quarks that do get confined. You cannot hold a top quark inside a proton because it refuses to survive long enough to be placed there. This makes the top quark a uniquely valuable research tool because it decays so quickly and so cleanly. Before the strong force can complicate its behavior with flux tubes and color confinement, physicists can study its properties in relative isolation. The top quark dies naked before the system surrounding it has time to dress it up in gluon fields. When top quarks were produced at Fermilab and later at the Large Hadron Collider, physicists measured their mass with extraordinary precision. Those measurements have become a critical test for the Standard Model, the rule book of physics. The mass of the top quark affects predictions for other particles in the theory, including the Higgs boson. The numbers have to agree. So far, they mostly do. But the top quark's extraordinary mass raises a question that physicists have not answered. Why is it so much heavier than the other quarks? The up and down quarks are nearly weightless by comparison. The top quark is tens of thousands of times heavier than an up quark. Something gave the top quark far more mass than anything else in its family, and the Standard Model can describe that mass but offers no explanation for why it is so extreme. That gap in understanding is one of the quiet alarms running beneath the surface of particle physics, and it points toward a broader problem with the rulebook itself, a problem that has started showing up in experimental data in ways that physicists are scrambling to explain. Color confinement has one known exception, one condition under which the flux tubes dissolve, the gluon cages melt, and quarks actually roam through space without being locked to any partner. Physicists call this state the quark-gluon plasma. It is the most extreme form of matter ever created by human hands, and the last time it existed naturally in the universe was roughly 1 millisecond after the Big Bang. To understand what quark-gluon plasma is, think about what heat does to ordinary matter. Ice is rigid. Water molecules lock into a crystal structure and hold their positions. Heat the ice and it melts. The molecules break free of their rigid arrangement and flow as liquid. Heat it further, and the molecules break apart entirely into water vapor, moving independently through open space. Now run that same logic down to the subatomic level. A proton is a rigid structure. 3 quarks locked together by gluon flux tubes, holding their arrangement the way ice holds its crystal, raise the temperature enormously, and the proton begins to soften. The gluon tubes lose their structure, raise it further, and the proton melts entirely. The quarks spill out. They no longer belong to individual protons or neutrons. They flow together in a shared collective state, a hot fluid where color charge moves freely across the entire volume rather than being trapped inside individual particles. The temperature required for this transition is 2 trillion degrees Fahrenheit. To put that in context, the The core of the Sun reaches about 27 million degrees Fahrenheit. Quark-gluon plasma requires a temperature roughly 70,000 times hotter than the center of our star. No natural object in the universe today reaches that temperature. The only place it exists is inside specialized particle accelerators for tiny fractions of a second, immediately before the cooling plasma snaps back into ordinary hadrons. What physicists found when they first created it surprised almost everyone. Before the experiments, many expected quark-gluon plasma to behave like a gas, hot chaotic particles flying in all directions. Instead, it behaved like a liquid, a nearly perfect liquid, with almost zero internal friction, flowing with a smoothness that no ordinary material can match. The quarks and gluons moved together in coordinated waves, responding collectively to the initial conditions of the collision. The quark-gluon plasma turned out to be the most perfect fluid ever observed in nature. That discovery changed how physicists think about the early universe. In the first millisecond after the Big Bang, all matter existed in this state. The entire universe was a plasma of free quarks and gluons flowing together as one perfect fluid, before cooling and snapping into the protons and neutrons that form all the matter around us today. Every proton in your body was once part of that plasma, and recreating it, even briefly, in a machine on Earth, requires conditions more extreme than anything found anywhere in the present universe. What that machine looks like, and what physicists saw when they turned it on, is a story unlike almost any other in the history of science. Sitting on Long Island, about 60 miles east of Manhattan, is a machine called the Relativistic Heavy Ion Collider. Most people have never heard of it. That is a shame, because what it does qualifies as one of the most extreme things humans have ever built. The machine is a circular tunnel roughly 2.5 miles in circumference. Inside that tunnel, 2 rings carry beams of gold atoms accelerated to 99.99% of the speed of light, traveling in opposite directions. When physicists aim those beams at each other, the gold atoms collide head-on at a combined speed approaching the speed of light itself. Why gold? Gold atoms are among the heaviest atoms that can be accelerated reliably. A gold atom contains 79 protons and 118 neutrons, meaning each collision brings hundreds of quarks into violent contact at once. The more quarks involved in a single collision, the more energy is deposited into a tiny volume of space, and the higher the temperature that brief region reaches. At full speed, the gold nuclei are so energetic that they are actually flattened by relativistic effects into disk shapes, compressed along their direction of travel. When 2 of these disks meet head-on, the collision is not like 2 marbles hitting each other. It is more like 2 clouds of pure energy overlapping for an almost immeasurable instant. The temperature at the point of collision reaches roughly 4 trillion degrees Fahrenheit, twice the temperature required to melt protons. In the moments after the collision, detectors surrounding the collision point record everything they can. Thousands of new particles spray outward in all directions. The detectors are layered like onion rings around the collision point, each layer recording different particle types, energies, and trajectories. The data from a single gold-gold collision can contain millions of individual particle tracks. From that data, physicists reconstruct what happened in the split second the plasma existed. The critical evidence that quark-gluon plasma had formed came from a measurement called jet quenching. In normal proton-proton collisions, high-energy quarks that get knocked loose produce jets of particles that travel outward and can be cleanly detected on both sides of the collision. In gold-gold collisions, one jet appeared as expected, while the jet going in the opposite direction was strongly suppressed, quenched. The plasma had absorbed it. That suppression was the fingerprint of a real dense medium. The plasma was thick enough and energetic enough to swallow an entire jet of particles. Nothing else in known physics produces that effect. The quark-gluon plasma was confirmed. and the temperature it takes to create that plasma points to a number so extreme it reshapes how we think about the universe and demands a closer look at exactly what 2 trillion degrees actually does to a proton. 2 trillion degrees Fahrenheit is a number that loses meaning the moment you try to compare it to anything familiar. The surface of the Sun is roughly 10,000 degrees. A bolt of lightning reaches about 50,000 degrees. The center of a nuclear explosion reaches hundreds of millions of degrees. These are extremes that already exceed anything in daily life by enormous margins. Quark-gluon plasma requires temperatures thousands of times beyond the center of a nuclear explosion. At 2 trillion degrees, individual particles carry so much energy that the gluon flux tubes binding quarks together simply cannot maintain their structure. The quarks inside protons and neutrons receive so much thermal energy that the strong force cannot keep up. The flux tubes dissolve. The protons and neutrons cease to exist as individual particles. Their quarks and gluons pour into a shared collective state. What scientists observed at the collider in New York confirmed something theorists had predicted, but physicists had never directly seen. The transition from ordinary matter to quark-gluon plasma is a phase change, similar in structure to water boiling into steam, but occurring at temperatures beyond anything in the present universe. The plasma itself lasted for an almost unmeasurably brief time, roughly the time it takes light to cross a single proton, multiplied by about 10. After that, the plasma cooled rapidly as it expanded, and the free quarks and gluons recombined into ordinary hadrons, spraying outward in all directions, as the detectors recorded their paths. One of the most unexpected findings was how the plasma flowed. Theorists had assumed that at such extreme temperatures, particles would behave like a gas, flying in random directions with no coordination. Instead, the plasma behaved like a liquid, with almost no internal friction. Physicists call this property low viscosity. Water has low viscosity compared to honey. The quark-gluon plasma has lower viscosity than anything ever measured, making it the closest thing to a perfect fluid that science has ever confirmed. The waves moving through the plasma during those collisions were recorded in the particle distributions spraying outward afterward. Physicists could literally read the ripple patterns in the particle data and reconstruct the fluid dynamics of a substance that no longer existed by the time the detectors fired. They were reading the wake of a vanished ocean of free quarks at temperatures that have not existed anywhere in the universe for 13 billion years. That ocean was the universe's original state. Everything you see around you, every star, every planet, every atom in your body, condensed out of that plasma in the first millisecond of existence. The question of why it condensed the way it did, why quarks snapped back into confinement so perfectly, why the rules held even at the moment the universe cooled from that extreme state, leads directly to one of the greatest unsolved problems in all of mathematics. Every experiment confirms it. Quarks are always found in groups. Alone they do not exist. Every measurement ever taken, every particle ever detected in every accelerator in history confirms that quarks travel together in combinations that produce color-neutral particles. The rule is called color confinement. It is the most consistently confirmed phenomenon in particle physics, and nobody can prove it. This is not a matter of missing data. Physicists have mountains of data. Color confinement shows up in every dataset from every high-energy experiment run over the past 50 years. The pattern is overwhelming and consistent. The rule clearly operates exactly as described. The problem is mathematical. Physicists have built a theory called quantum chromodynamics that describes how quarks and gluons interact. The theory works extraordinarily well. It makes predictions that match experimental measurements to extraordinary precision. Physicists use it to calculate the masses of protons, the behavior of quarks at different energies, the properties of quark-gluon plasma. The calculations match reality. But quantum chromodynamics cannot, in its current mathematical form, prove from first principles that confinement must occur. The theory describes what happens. It cannot yet derive why confinement is a necessary consequence of the mathematics, rather than just a feature of how the equations happen to work at low energies. To put this simply, the rulebook works perfectly, but the explanation for why the most important rule in the book exists has not been written yet. Physicists can simulate confinement using immense computing power. A technique called lattice quantum chromodynamics divides space into a fine grid and runs calculations at each point, simulating how the color field evolves over time. These simulations reproduce confinement precisely. They show the flux tubes forming, the quark pairs popping into existence, the system maintaining its color-neutral structure through every perturbation. But a simulation confirming a pattern is different from a mathematical proof that the pattern must exist. The gap between those two things, between observational confirmation and mathematical proof, is one of the most consequential open problems in science. Filling it would require a fundamental advance in understanding the mathematics of quantum field theory, the framework describing how all particles and forces behave. Someone who fills that gap will not just answer a physics question. They will have developed new mathematics capable of describing a force that no existing tools can fully capture. The prize for solving it is waiting. In the year 2000, the Clay Mathematics Institute in Cambridge, Massachusetts, published a list of 7 mathematical problems. These were not ordinary difficult problems. They were problems that the mathematical and scientific community had worked on for decades, in some cases centuries, without success. Problems so deep that solving any one of them would fundamentally change human understanding of mathematics or physics. Each problem came with a prize of $1 million. One of those 7 problems is directly about quarks. The problem is formally called Yang-Mills existence and mass gap. The Yang-Mills equations are the mathematical framework underlying quantum chromodynamics, the theory of quarks and gluons. The first part of the challenge is to prove that these equations have mathematically consistent solutions in 4-dimensional space, the space we actually live in. The second part, the mass gap, connects directly to confinement. The mass gap refers to the fact that all particles produced by the strong force have a minimum mass. There are no massless particles carrying the strong force over long distances, the way photons carry electromagnetism across the entire universe. This minimum mass is what causes the strong force to drop off at distances larger than a proton's width, trapping its effects inside atomic nuclei. Proving mathematically that the Yang-Mills equations necessarily produce a mass gap would also explain why confinement occurs. It would show from pure mathematics that a force governed by these equations cannot allow lone quarks. It would transform color confinement from an experimentally observed pattern into a mathematically proven necessity. No one has done it. The prize sits unclaimed. The problem remains open. Mathematicians and physicists have made progress in specific cases and limited dimensions, but the full proof in 4 dimensions, the real universe, remains out of reach. The reason it is so difficult is that the equations describing the strong force become extremely complex at low energies, which are the energies relevant to confinement. At high energies, the mathematics of asymptotic freedom makes the equations manageable. At low energies, the coupling between quarks and gluons becomes so strong that the standard mathematical tools used in quantum field theory stop working reliably. Solving this problem would require entirely new mathematical methods. Whoever manages it will have understood something about the fabric of reality that has resisted every attempt by the best mathematical minds in the world for over 50 years. That prize is a direct measure of how deep the mystery goes. And the mystery does not stop at confinement. The equations describing quarks have also started producing results that do not match what the rulebook predicts, results coming out of the most powerful physics experiments on Earth right now. Physicists built the Standard Model over several decades, finishing its core framework in the 1970s. It is the most precisely tested scientific theory in history. The Standard Model describes all known fundamental particles, and 3 of the 4 fundamental forces. It predicted the existence of the top quark, the Higgs boson, and numerous other particles before any of them were detected. When those particles were found, they matched the predictions with extraordinary accuracy. In some cases, the Standard Model's predictions have been confirmed to a precision of 1 part in a billion. No other theory in science comes close to that record. But the Standard Model has problems. It says nothing about gravity. It gives no explanation for why particles have the masses they do. It cannot account for dark matter or dark energy, which appear to make up the overwhelming majority of the universe's total content. It describes only the roughly 5% of the universe made of ordinary matter, and even within that 5%, cracks are appearing. The cracks involve quarks specifically. Starting in 2011, measurements at the Large Hadron Collider began showing deviations from Standard Model predictions in the behavior of particles containing bottom quarks. The deviations were small. Each individual measurement could have been a statistical fluke, but over the following decade, as more data accumulated and more experiments ran, the deviations kept appearing. They clustered around the same types of processes, the same particles, the same quark flavors. A pattern was forming where there should have been none. The Standard Model makes a specific prediction called lepton universality. It states that the weak nuclear force, which governs certain types of particle decay, treats electrons and muons identically. Muons are heavier versions of electrons, but aside from their mass, the laws of physics should apply to them equally. The force should not prefer one over the other. Experiments were starting to suggest the force had a preference. Bottom quarks were decaying into electrons more often than into muons. The difference was small but consistent across multiple experiments. If real, it meant something was interfering with the decays in a way the Standard Model did not account for. Something new. Something the rulebook did not include. The physics community grew cautious. Extraordinary claims require extraordinary evidence. The data was interesting, but the margins of uncertainty were still wide enough to keep the results in the category of hints rather than confirmed discoveries. Then a separate experiment, measuring something completely different, found its own deviation, and the two anomalies pointed in the same direction. In 2021, physicists at the Large Hadron Collider published a result that shook the particle physics community. The experiment was called LHCb, a detector specifically designed to study particles containing bottom quarks. These particles are called B mesons. A B meson is a quark-antiquark pair, one of which is a bottom quark. They are unstable, decaying rapidly into other particles through the weak nuclear force. The Standard Model makes a precise prediction about how often B mesons should decay into particles containing electrons versus particles containing muons. The prediction is clean. Electrons and muons should appear at the same rate, within a small correction for their mass difference. The ratio should be very close to 1. The LHCb detector measured the ratio. It came out at roughly 0.85. Muons were appearing about 15% less often than electrons in these decays. 15% is a substantial deviation across hundreds of millions of recorded collisions, providing an enormous statistical sample. The deficit was consistent. The measurement carried a statistical significance that physicists described as one of the most intriguing results the Collider had produced in years, significant enough to take seriously. Not yet at the threshold physicists require to claim a discovery, 5 sigma, meaning the result would occur by random chance only once in roughly 3.5 million trials. But the direction of the deviation was clear. Something in the decay process was suppressing muons. The Standard Model offered no explanation. According to the theory, this suppression should not exist. The weak force treats leptons, the family of particles that includes electrons and muons, without preference. Lepton universality is a core feature of the model, supported by decades of measurements across dozens of experiments. One measurement showing a 15% deviation could be noise. Systematic experimental error. a misunderstood background process. These alternatives all remained possible. What made the result genuinely alarming was its consistency with earlier independent measurements, showing similar patterns in different decay channels. The LHCb result was not the first anomaly involving bottom quarks and leptons. It was the latest in a series of hints, accumulating across multiple experiments and multiple particle types, all of them pointing to the same gap in the rulebook. If the deviation was real, it implied that something beyond the standard model was actively interfering with how bottom quarks decay. A particle or force not listed in the theory was reaching into the decay process and pulling muons off the predicted path. Identifying that interference requires understanding exactly what lepton universality means and why physicists trusted it so completely for so long. Electrons are familiar. They orbit atoms, carry electric current, and enable every device running on electricity. Muons are less familiar, but structurally almost identical. Same electric charge, same spin, same interactions with every known force. The only significant difference is mass. A muon weighs about 200 times more than an electron. Outside that mass difference, every equation describing an electron should apply equally to a muon. This equivalence is called lepton universality. The universe, according to the standard model, applies its rules without mass preference in the lepton family. Forces do not care whether they are pushing on an electron or a muon. The interactions proceed identically, adjusted only for the mass difference. Lepton universality is not a guess or an approximation. It is a structural feature of the standard model, built into the equations at a fundamental level. If lepton universality breaks, the equations need new terms. New terms mean new physics. New physics means either the standard model is incomplete or something entirely new is operating in nature. For decades, every measurement confirmed universality to high precision. Experiments involving the weak nuclear force, the force responsible for radioactive decay and for making particles like B mesons fall apart, consistently showed electrons and muons being produced at the predicted rates. The rulebook held. Then the B meson measurements started diverging. Bottom quarks decaying into final states, with muons appeared less often than predicted. The suppression was not random. It targeted muon-containing decay channels specifically. Electron-containing channels held steady. Whatever was pulling the muons off course was not disturbing the electrons. That selectivity is important. A systematic experimental error would typically affect all measurements somewhat equally, or at least not discriminate so specifically between particle types. A detector problem affects detection efficiency across the board. A misunderstood background process contaminates multiple channels. The pattern of muon suppression specifically in bottom quark decays was difficult to explain with mundane errors. The most natural explanation within physics is that something beyond the standard model is coupling preferentially to muons, some particle or force that the theory does not include, which interacts with muons more strongly than with electrons, and interferes with the decay rates. Two candidates for that unknown particle emerged from theorists almost immediately after the anomalies became public. Both candidates, if proven to exist, would require additions to the standard model significant enough to reshape fundamental physics. Both have names, and both are currently being searched for in the data from accelerators around the world. In 2025, a team at the Thomas Jefferson National Accelerator Facility in Virginia published a result that landed on top of the existing anomalies like a second alarm going off. The experiment fired high-energy electrons at two targets, pure hydrogen, which contains single protons, and deuterium, which contains protons bonded to neutrons. By comparing how the electrons scattered off both targets and how the quarks inside fragmented into new particles afterward, the team could compare the behavior of up quarks inside protons to down quarks inside neutrons directly. The standard model makes a specific prediction here based on a property called charge symmetry. Charge symmetry states that if you take a physical system and swap all positive charges for negative and all negative charges for positive, the underlying physics should remain the same. Applied to quarks, this means an up quark inside a proton should behave identically to a down quark inside a neutron, because swapping the charges converts one into the other. The fragmentation patterns, the way those quarks break apart and produce new particles after being struck, should be mirror images. They were not. Up quarks and down quarks fragmented differently. The distributions of particles they produced after being hit by high-energy electrons were measurably distinct. The charge symmetry that the Standard Model treats as a fundamental property of quark interactions had broken down in the experiment. The team was careful. They checked for systematic errors. They modeled alternative explanations. They examined whether detector effects or target differences could account for the discrepancy. After accounting for everything they could identify, the asymmetry remained. The result added a second and independent crack to the Standard Model's surface, originating from a completely different type of experiment, measuring a completely different quantity, at a completely different facility from the Large Hadron Collider results. Two separate experiments, two separate anomalies, both involving quarks behaving in ways the rulebook says they should not. The physics community took notice. Individual anomalies can be flukes, two independent anomalies pointing toward the same conclusion, that the Standard Model's symmetry assumptions about quarks are incomplete, carry a different weight entirely. The specific symmetry breaking seen at Jefferson Lab pointed toward an effect that could only be explained by new physics, acting differently on up quarks than on down quarks, or by some unknown modification of how quarks fragment into particles when struck. Either possibility requires something the Standard Model does not contain, and two specific theoretical candidates have been proposed to explain both sets of anomalies simultaneously. Candidates so exotic that confirming either one would produce the biggest shift in fundamental physics since the Standard Model itself was completed. Charge symmetry is one of the foundational assumptions of particle physics. The idea is simple at its core. Physics should look the same if you swap every positive charge for a negative charge and every negative charge for a positive charge. Flip the signs on all charges everywhere in a system, and the rules governing what happens next should remain identical. The same forces, the same interactions, the same outcomes. This is not an arbitrary assumption. It follows from deeper mathematical structures in quantum field theory. The Standard Model's equations are built to respect charge symmetry as a natural consequence of their structure. It is not something physicists added because they wanted it to be true. It falls out of the mathematics automatically. So when an experiment finds that up quarks and down quarks, which are charge partners of each other, fragment differently after a high-energy collision, the Standard Model has no built-in explanation. The rulebook says the fragmentation should be symmetric. The data says it is not. There are two broad categories of explanation. The first is that the Standard Model is simply missing a term. Some interaction that physicists have not accounted for is applying force differently to up quarks than to down quarks, breaking the symmetry from the outside. Something real and physical is in the system, but absent from the theory. Adding the right term to the equations would restore the ability to predict the experimental result, but the term itself would represent new physics, new particles, or new forces. The second category is more radical. Perhaps charge symmetry is approximate rather than exact. Perhaps the universe does not perfectly preserve the symmetry when charges are swapped. This would mean the mathematical structure of the Standard Model, built around exact symmetry, is a very good approximation of reality, but not a complete description of it. The actual laws of nature might be slightly asymmetric in ways that only show up in extremely precise measurements. Both possibilities have dramatic implications. In the first case, physicists need to find and identify the new particle or force causing the symmetry breaking. That requires more experiments, more data, more collision energy. In the second case, the mathematical foundation of the theory needs rebuilding. a project that would take decades and reshape the entire field. The experiments at Jefferson Lab and the Large Hadron Collider are not just collecting data about quarks, they are testing whether the framework humans use to describe reality at its most fundamental level is the right framework. Every deviation from prediction is a signal that the map does not perfectly match the territory. The candidates proposed to explain the map's failures have names that sound like science fiction. One of them might be real. Quarks and leptons are separate families. Quarks build protons, neutrons, and the particles produced in high-energy collisions. Leptons are particles like electrons, muons, and neutrinos. In the Standard Model, quarks and leptons interact indirectly through the force-carrying particles that mediate the fundamental forces. They do not couple directly to each other. A leptoquark would change that entirely. A leptoquark is a hypothetical particle that carries both quark properties and lepton properties simultaneously. It would interact directly with a quark and a lepton at the same vertex, coupling them in a way the Standard Model does not permit. If a leptoquark exists, it acts as a bridge between two families of matter that the current rulebook treats as completely separate. Here is why leptoquarks are the leading candidate for explaining the bottom quark anomalies. When a B meson decays through the weak nuclear force, it should produce electrons and muons at equal rates, because the weak force treats them identically. The deficit in muon production implies something is interfering with the muon channel. A leptoquark with a strong coupling to muons and bottom quarks would do exactly this. It would participate in the decay process, adding an additional interaction that competes with or suppresses the standard weak force decay into muons. The interference would be invisible unless you looked at the ratio of electron to muon production rates very carefully, which is exactly what the LHCb experiment did. Leptoquarks are also consistent with the Jefferson Lab charge symmetry breaking result. If a leptoquark couples differently to up quarks than to down quarks, it would alter the fragmentation patterns of those quarks in precisely the direction the experiment observed. One particle, two anomalies. The fit is appealing. Leptoquarks are not a new idea. Theorists proposed them in the 1970s as a natural feature of certain grand unified theories, models attempting to merge the strong force, the weak force, and electromagnetism into a single mathematical framework. In those models, quarks and leptons are not truly separate families. They are different aspects of a single underlying type of matter, and leptoquarks are the particles that reveal the connection. If a leptoquark is detected at the Large Hadron Collider or at a future accelerator, it would be the first direct evidence that quarks and leptons belong to the same family. The boundary between those two groups of particles, which the Standard Model treats as fundamental and permanent, would turn out to be an artifact of low energy. At higher energies, the boundary dissolves. The Standard Model would need to be extended or replaced. But leptoquarks are one of two serious candidates on the table. The other one works through a completely different mechanism, involving a new force carrier so heavy that current accelerators may not be powerful enough to produce it directly. In the Standard Model, forces are carried by particles. The electromagnetic force is carried by photons. The weak nuclear force is carried by particles called W bosons and Z bosons. The strong force is carried by gluons. Each force has its associated carrier, and together they account for all known particle interactions. Theorists have proposed that a fourth neutral carrier exists beyond the Standard Model's Z boson. They call it the Z prime boson. The Standard Model's Z boson mediates the weak nuclear force and interacts with all quarks and leptons in a specific symmetric way. A Z prime boson would be heavier, much heavier, and would couple to particles differently from the Z boson. Specifically, theorists have built models where the Z prime boson couples more strongly to muons and to bottom quarks than to other particles. It would be a force carrier with a preference, an asymmetric interaction profile that the Standard Model's particles do not have. If such a particle exists, it would show up as a hidden influence in particle decays. When a bottom quark decays, The Z-prime boson would participate in the process alongside the standard weak force carriers. Because the Z-prime couples more strongly to muons than to electrons, its participation would alter the ratio of muon to electron production. Bottom quarks decaying through the Z-prime channel would produce fewer muons than the standard model predicts, exactly the deficit that LHCb measured. The challenge with the Z-prime boson is mass. Models that fit the anomaly data tend to predict that the Z-prime would be very heavy, likely too heavy to produce directly at the Large Hadron Collider at its current energy. This is simultaneously the reason the particle has not been found, and the reason its effects might only show up indirectly in the subtle statistical shifts of decay rates, rather than in direct particle production. Physicists call indirect searches like this the low-energy frontier. Rather than building a machine powerful enough to create the new particle directly, they use precision measurements at lower energies to detect its influence through quantum corrections. The Z-prime boson, if it exists, would leave fingerprints in the data, even if the particle itself is too heavy to appear. Both the Z-prime boson and the leptoquark represent new physics that extends beyond the standard model. Both fit the current anomaly data well enough to be taken seriously. Both make predictions that future experiments can test. The two candidates are currently being probed simultaneously at the Large Hadron Collider and at planned future colliders. One of them might be real. Both might be wrong. Or the answer might be something theorists have not yet imagined. What makes the stakes of this search so high is not just the physics. It is what these particles would mean for technology, medicine, and the stability of every device built on the assumption that the standard model is complete. Physics discoveries can feel remote, particles too small to see, forces operating at scales thousands of times smaller than atoms, experiments running in tunnels beneath mountains in Switzerland or on Long Island. The gap between particle physics and daily life seems enormous. It is an illusion. Every piece of technology you use runs on the assumption that the standard model's rules are stable and predictable. Every semiconductor chip, every MRI machine, every nuclear reactor, every laser, every radio signal, all of it is engineered based on precise knowledge of how particles and forces behave. MRI scanners work by manipulating the magnetic properties of hydrogen nuclei, individual protons, responding predictably to magnetic fields. The design of every MRI machine in every hospital in the world depends on the proton behaving exactly as the standard model says it should. If the rules governing quarks inside those protons were different from what the model predicts, the machines would not work as designed. Nuclear reactors control the energy released when heavy atomic nuclei split. That split releases energy because of the difference in binding energy between the original nucleus and its fragments, energy stored in the color force holding quarks together. Every safety calculation, every fuel cycle design, every power output estimate in a nuclear reactor is built on standard model predictions about strong force binding energy. Computer chips rely on the behavior of electrons in semiconductors. Electrons are leptons, and lepton universality is precisely the assumption currently under experimental pressure. If muons and electrons truly behave differently in some interactions, the mathematical framework used to model electron behavior in semiconductors needs re-examination at fundamental levels. These are not immediate practical concerns. Current technology operates well within the energy ranges where the standard model's predictions are rock solid. The anomalies showing up in high-energy experiments involve processes at energies far beyond anything relevant to consumer electronics or power plants. But the history of physics shows that fundamental discoveries always eventually transform technology. Quantum mechanics seemed like abstract theory in the 1920s. Within 30 years, it produced the transistor, the laser, and eventually every device running on a chip. Understanding the strong force-produced nuclear energy and medical imaging, every layer of reality physicists uncover eventually becomes an engineering resource. If a leptoquark or a Z-prime boson is real, understanding it will produce new mathematics describing a deeper layer of reality. That mathematics will eventually describe new particles, new interactions, new principles. Technologies built on those principles are not predictable from where we stand today, just as no one in 1920 could have predicted the smartphone. The quarks are not just academic, they are the foundation, and that foundation is stranger than it looks, even at the level of what sits inside a proton right now. A proton contains 3 quarks. That sentence appears in textbooks, on educational websites, in science documentaries. It is true, and it is also, in an important sense, deeply incomplete. At any given moment inside a proton, the 3 quarks you learned about, called valence quarks, share their space with a constantly shifting population of additional particles. Virtual quark-antiquark pairs flicker into existence from the energy of the gluon field, persist for an immeasurably brief moment, and then annihilate back into energy. They leave no lasting trace, but while they exist, they are real. They have mass. They carry color charge. They interact with the valence quarks and with the gluons streaming around them. Physicists call this the sea of virtual quarks. The sea is not empty between pulses. It is more accurate to picture the interior of a proton as a constantly churning fluid, with pairs of quarks and antiquarks appearing and dissolving at rates far too fast to track individually, like the surface of water boiling rapidly. The 3 valence quarks ride through this fluid, affecting it and being affected by it. This sea has measurable consequences. When physicists fire high-energy electrons at protons and map where the electron bounces off, they detect scattering events that cannot be explained by 3 valence quarks alone. Occasionally, an electron hits what appears to be a quark, carrying a tiny fraction of the proton's momentum, far less than any valence quark should carry. These low-momentum quarks are members of the virtual sea, temporarily real enough to interact with the electron before dissolving back into the field. The sea also contains quarks of all 6 flavors, including charm and strange quarks that are heavier and far rarer than the up and down quarks dominating the valence structure. At high enough energies, the gluon field has enough energy to briefly spawn charm quark-antiquark pairs or strange quark-antiquark pairs inside the proton. These heavier virtual quarks appear and vanish even more quickly than the lighter sea quarks. The exact composition of the quark sea at different energies is an active area of research. Mapping the sea, understanding how many virtual pairs of each flavor exist at a given energy scale, how they are distributed across the proton's volume, and how they influence the proton's overall properties, requires experiments precisely measuring the momentum distributions of quarks struck by high-energy probes. The Jefferson Lab experiment that detected charge symmetry breaking was partly measuring asymmetries in this sea, comparing how up quarks and down quarks appear in the virtual sea of neutrons versus protons. The sea is not perfectly symmetric between flavors. Up quarks and down quarks exist in slightly different ratios in the virtual sea, and that asymmetry feeds directly into the experimental measurements probing the standard model's limits. Inside every proton in your body, this invisible storm runs continuously. 3 permanent quarks, surrounded by a shifting cloud of thousands of virtual ones, all maintained by 8 types of gluons, operating at scales and energies beyond any instrument humanity has built. And those gluons themselves carry a complexity that mirrors the quarks they bind. Gravity has 1 carrier. The graviton, theorized but never directly detected, carries the gravitational force. The photon, every radio wave, every beam of light, every X-ray is a stream of photons. The weak nuclear force has 3 carriers, the W+ boson, the W- boson, and the Z boson. The strong force has 8 distinct types of gluons, each carrying a different combination of color and anti-color charge, together form the complete set of carriers needed to transmit the strong force between all possible color charge combinations. The number 8 comes directly from the mathematics of color charge. 3 colors and 3 anticolors create 9 possible combinations. One of those combinations is color neutral and does not participate in the strong force. The remaining 8 do. giving the strong force its 8 carriers. This is already more complex than any other force, but the complexity goes deeper. Because gluons carry color charge, they interact with each other. Photons, the carriers of electromagnetism, pass through each other without interaction. 2 beams of light can cross in the same space and emerge completely unchanged. Gravity works similarly. Gravitational waves travel through each other without altering their paths. Gluons cannot pass through each other. 2 gluons moving through the same space will interact, exchange color charge, and change each other's trajectories. The force carriers participate in the force they carry. This self-interaction is called a non-abelian property of the field, named after the mathematician whose work on group symmetry describes it. The self-interaction of gluons is the direct cause of asymptotic freedom. As quarks get closer together, the gluon field between them becomes denser, and the self-interactions between gluons become more significant. At very short distances, the gluons spend so much of their energy interacting with each other that the coupling between the quarks weakens. At longer distances, the gluon self-interactions organize the field into the concentrated flux tube that holds the quarks with constant force. A single property, gluons attracting each other, produces both asymptotic freedom at close range and color confinement at longer range. One mathematical feature generates the 2 most distinctive and counterintuitive behaviors of the strong force simultaneously. Theorists also predict that gluons can form bound states with each other, particles made entirely of gluons with no quarks involved. These are called glue balls. Nobody has definitively detected one yet, though several particle candidates have been proposed and are actively being studied. A glue ball would be a form of matter made purely of force carriers, something with no analog in electromagnetism or gravity. The 8 gluons, their self-interactions, and their potential to form pure gluon-bound states make the strong force the most mathematically rich and experimentally demanding of all the fundamental forces. Understanding it fully, from the flux tubes holding protons together to the glue ball candidates appearing in accelerator data, requires tools at the edge of both experimental physics and pure mathematics. And those tools are pointing toward a future where the Standard Model is only the beginning of the story. The Standard Model is extraordinary. It describes every particle ever detected. It predicted dozens of particles before they were found. It has survived 50 years of experiments designed to break it. Its precision in certain measurements is unmatched by any other scientific theory in history, and it is almost certainly incomplete. Physicists have known this for decades. The Standard Model says nothing about gravity, the force shaping galaxies and holding planets in orbit. It has no room for dark matter, the invisible substance whose gravity holds galaxies together despite accounting for no particles in the model. It gives no explanation for why the universe contains matter, rather than equal amounts of antimatter, which should have formed in equal quantities at the Big Bang and annihilated all the matter we see. These are large structural gaps. They were known before the bottom quark anomalies appeared. They are the reason physicists have been searching for new physics for decades. What the recent quark anomalies add is something different. Evidence that the cracks in the Standard Model might be accessible, measurable, specific enough to build toward. The bottom quark decay asymmetries and the charge symmetry breaking at Jefferson Lab are not vague signals lost in noise. They are patterns appearing consistently across multiple experiments, pointing to specific types of new physics with nameable candidates. If a leptoquark is confirmed, it tells physicists that quarks and leptons are unified at high energies, that the boundary between them is an artifact of the low-energy world we inhabit. The next theory would include a deeper symmetry group containing both families, and physicists would begin building the mathematics to describe it. If the Z-prime boson is found, it tells physicists that a fourth neutral force carrier exists beyond the Standard Model, meaning the list of fundamental forces and their carriers is longer than currently believed. The model describing 3 forces would expand to include a fourth interaction, and the energy scales at which these new forces operate would map out new territory for experimental exploration. If both candidates fail and the anomalies turn out to have a different explanation entirely, that outcome is equally valuable. It would eliminate two theoretical directions and force theorists toward genuinely new frameworks. Progress in physics has always moved through elimination as much as confirmation. What comes after the standard model has been theorized for decades. String theory attempts to unify all forces by describing fundamental particles as vibrating strings of energy. Loop quantum gravity tries to unify quantum mechanics with Einstein's description of space-time. Grand unified theories propose that all three non-gravitational forces merge into one at extremely high energies. None of these have yet produced predictions confirmed by experiment. The quarks may lead the way forward. They break rules, they generate anomalies, they sit at the center of the deepest unsolved problems in mathematics. They make up almost everything you can touch, see, and interact with, while remaining permanently hidden from direct observation. The particles that build reality refuse to be seen alone. And somewhere in that refusal, in the mathematics of why confinement exists and what lies beyond the rules it enforces, is the next layer of understanding, the one that changes everything again, the way every deep discovery in physics has, from atoms to nuclei to quarks, each time revealing a universe stranger and richer than the one before. The quarks are waiting. The experiments are running. The next rewrite has already begun.